Hello, good day. We'll be discussing about lithography today. Okay, so you might have already seen the processes where we have silicon wafer on which we might have spin coated a thin layer of polyimide, which is a flexible substrate, right? And it's baked and cured so that it can be used for the next step, which is electrode fabrication. Okay, now when we talk about a neural interface, mostly it will have a substrate which can be silicon or an electrode base of gold or platinum or one of the metals like that. Now the substrate can be silicon or polyimide, and the conductive lines through which the data is collected can be gold or platinum or any other conducting material. Now there are a lot of other surface modifications that can be done as well if we are planning for stimulation of the brain as well. Now for our course, we'll be showing mostly for device fabrication that can be used for neural recording mostly. Okay, so we will see how the process is happening. Now if we have a substrate, okay, and we need to create electrodes which can be used for recording, there are multiple steps involved in it. So first the substrate will be there. One approach could be, which Professor Hardik might have already taught you, is that on the substrate we can deposit metal, okay, say gold or platinum or titanium gold or titanium platinum. That metal can be deposited, followed by pattern transfer using lithography process. Okay, once this pattern is transferred, okay, we can etch off the excess metal to realize the electrodes. Now that is one approach to do lithography and creation of electrodes or the features that we need. Another alternative approach is, what we can do is to have the substrate, we can do lithography first, right, and transfer the pattern, followed by deposition of metal. Now what happens in this case is that when we transfer the pattern before metal deposition, the patterns will be designed such that the openings will be there where the metal can get deposited, okay, which forms the electrode later on. Okay, and wherever there is no opening of the photoresist and the metal is there, which will be removed during the next step, which is known as lift-off. So there are two alternative methods during lithography where we can realize metal contacts. One is a lift-off approach where we do photolithography first and pattern the photoresist, followed by metal deposition, and then do the lift-off process where the excess metal is removed, okay, by removal of photoresist. Alternate approach is deposit metal first, then go for photolithography, so that you can use the photoresist as a mask for etching. So either of these processes can be done. Now when we are using a flexible substrate, it is ideal to use one approach over the other. Okay, so based on our device requirement, we are doing a lift-off process. So what you would see today is that on the polyimide substrate that we have, or polyimide substrate which was spin coated on the silicon wafer, okay, we will be doing photolithography for transferring the pattern. Then we will see how e-beam evaporation can be used for depositing metal, and which further can be taken to lift-off, so that we will get the metal lines. So we will see the process. Now, we have earlier seen the processes where we have seen how the wafer is cleaned, and and processes like that, or the pre-processing, and which you might have observed that happens in a room which is white, or there is white light, like the place where I am standing. Now behind me, you can see a room which is yellow in color. So this is known as a yellow room, okay, where the lithography has to happen. Now why this room is necessary? So if you think about it, photolithography itself means that, okay, there is some light dependence there. Okay, photolithography. Now lithography is basically patterning, okay, and photolithography means patterning with the help of light. Okay, so this is a process that have been evolved long back. So one of the example that you might be aware already is where photography is used. So there used to be film-based photography back in the days, right? And there used to be a film where there is negative and other things like that. You might have seen, before. Maybe like 20 years back, those kind of photography films were there. Now, for processing that film to the photograph that we need, or the printed paper, on the printed paper, a similar principle was used. And you would have seen in movies or something where they show a photographer processing their photo. They might have used a room like this, yellow room. Okay, so why we do this, or even for photography or photolithography, why do we need a yellow room? So the thing is that for photolithography to happen, we use a specific material known as photoresist, which you might be already aware through the other lectures that you had already. So this photoresist is light sensitive. Okay, so what light sensitive means is, this photoresist is the material, if light falls on it, especially if UV light falls on it, its property changes. So consider this like a fluid kind of material, which is like a paint. Assume photoresist like a paint, which we coat on a substrate using a process known as spin coating. Okay, so we have a thin fluid coating over the substrate that we need. Okay, now we dry it. Okay, so that's known as soft bake. Okay, or pre-bake. So that's one step. Now after that, after the pre-bake, what we have to do is we will do the lithography process. Now after pre-bake, when you do the lithography, okay, the areas where the light falls can become soft or hard based on the property of the photoresist. Now say when I say okay, the photoresist becomes hard, what it means is that when you put in a solution known as developer, okay, the photoresist that is hard remains there, and rest of the soft photoresist will go away. Okay, so it's like if this is a finger, okay, and I have the substrate with photoresist coated kept here, and the light source comes from here. Okay, then the light passes through these gaps in the fingers and falls on the substrate. Now wherever the light fell might have a different property than that of wherever light has not fallen. Okay, so this is the principle of photolithography, and we will further see how this actually happens. Now as I said, the photoresist might have different properties. It can, they are mostly classified into positive photoresist and negative photoresist. Now, when I say positive photoresist, what it means is that, say, if this my fingers are the mask, okay, so this is the opaque region, and this is the transparent region, right? The light can pass through, the light cannot pass through, and I have the substrate here with the photoresist, which is positive. Then if the light passes through here and falls on the substrate here, what we would have is, if it's a positive photoresist, is wherever light has fallen, it will become a soft region. Okay, when I say it's soft region, what means is, later on during a process named as development, the photoresist which was exposed to light will go away, or it will get removed. Okay, now if it is a negative photoresist, okay, if it is a negative photoresist, what happens is, wherever light has fallen will become strong and it stays there. So this is two different types of photoresist that we will be using. Now for our specific use case, we will be using a positive photoresist. That means if light falls, it will get removed, or it will become soft. Okay, now we will see two different type of mask, and I will also show you maybe a couple of types of photoresist in the bottle. But for our use case, we will be using a positive photoresist. Now let's go to the yellow room. So now we are inside the yellow room. You can see the overall color difference, right? So now I have talked about positive and negative photoresist. Now I will show you something known as a bright field and a dark field mask. Okay, so these are masks, okay, or photo mask. See, do you notice the difference between these two? Maybe I can show it against a surface. Do you see the difference between these two? Okay, so if you look here, you can see the within the circle, it's more or less transparent, right? You might be able to see small features there as well, right? Okay, so those are the pattern that we need. Okay, so these are the pattern that we need, but most of the area is kind of transparent. Now if you look at this mask, okay, you can see that most of the areas are dark and some patterns are there which are transparent in nature, right? So what's the difference between these two masks? So we would call this one as a bright field mask and this one as a dark field mask. All right, so we have seen a bright field mask and a dark field mask. So depending on the requirement that we have, we would change the mask. Now think about it like this. we have two different type of mask, which is like bright field and dark field, and then we have two different type of photoresist which can be positive or negative. So you can think of the possible combinations in which you can create a pattern onto the wafer or the substrate or the photoresist, right? So if you think it like this, okay, so this is a bright field mask, right? This is a bright field mask, and we have the wafer with photoresist here, which is a a negative photoresist. Okay, if it is a negative photoresist, what happens? The light passes through the transparent area, right, and falls onto the photoresist which is negative. Now you know that negative photoresist, what happens is if the light falls, that area becomes hard, right? So wherever the transparent areas were there you will have hard photoresist, and wherever the light didn't pass, okay, it will have soft photoresist. Now this combination, that a bright field mask and a negative photoresist, can be used for lift off. Why so? Because the patterns that we need is where the metal should come, right? So when we have photoresist and it is exposed, right, so the soft areas, which are the patterns, will get removed during the development process, and when we deposit the metal in those gaps in photoresist, the metal will get deposited. So that's a lift off process. Now if you look at a dark field mask, okay, to get the same effect, what we have to use is a dark field mask coupled with a positive photoresist. Then what happens? The light passes through the pattern, right, and falls on the positive photoresist, and wherever light is there the photoresist becomes soft. So the pattern areas that we need will get the photoresist get removed, and we can deposit metal. So in today's process we will be using this photo mask, okay, coupled with a positive photoresist, so as to get the lift off feature that we need. Now I will show you two different type of photoresist so that you will understand what they are. Okay, so I told you there are positive and negative photoresist, right? And this is an example of a positive photoresist, which is AZ 4562. Okay, this is a positive photoresist, and what most of the photoresist with this number like this, say 4562, has something associated with this number 4562 has something associated with its properties. So what it means is that the coating procedure or the spin coating procedure that we use for this photoresist is somewhat evident from this number. So the 62 at the end means that when we spin coat this photoresist at the recommended RPM or rotation speed, you will get a thickness of photoresist equal to 6.2 micron. So this is a very repeatable process. Now when we are spin coating, depending on the speed at which we rotate, okay, or the acceleration that we do, and the duration at which we do the spin coating, the thickness might vary. But for the recommended speeds, it would be 6.2 micron. Now then we have a negative photoresist, okay, which is NLOF 2020, okay. So this is another photoresist which is negative in nature. So for our today's use case, we will be using a positive photoresist which is known as 3012. So I will show you that now. So this is the 3012 photoresist, okay. So as you might already know now, 1.2 micron is the thickness that we will get if we spin coat this photoresist at the recommended RPMs. Now these photoresists, the bottles has to be stored between 0 to 25 degrees Celsius, preferably in a freezer, okay. And for the convenience, we will be transferring the photoresist onto a smaller, dark bottle where the light doesn't go in. So here we can store and use it for the later use. So I will be using photoresist from this bottle during the experimentation that I will be showing. So now this is the fume hood where we have to do the spin coating of the photoresist. Okay. Now photoresist is a biohazardous material, okay, and which is reported to be carcinogenic. So we need to take enough preventions, right, or precautions to so that there is no health hazard to us. Okay, so this is the fume hood. Okay, if we close the fume hood lid like this, the laminar flow that is installed within the fume hood will prevent any volatile gases to come outside. So there are the photoresist, as I said, is a fluid like material, right? So the solvent will evaporate so that it gets hard, or the photoresist gets hard by the evaporation of solvent, So to prevent ourselves from breathing in the solvent, we use a fume hood all the time. Now, right now we haven't spin coated the photoresist. So if you look here, the main tools that we need for spin coating are, one, this is the spin coater that we have, right? Then we also have hot plates for baking the photoresist. I will talk about the processes on the way. Okay. Now we will first prepare the spin coater for spin coating. Okay. So this is the lid of the spin coater. Okay, which I'm keeping it here, and this is where we load the sample. Now you can see that, okay, there is a chuck. This is known as the chuck, okay, which is able to rotate, right? And you can see a few grooves here, right? Circular grooves with a center hole here. Okay, now the point of the chuck is when we load the wafer onto the circular chuck through vacuum suction, okay, this the sample will be held here. Since we are going to rotate the wafer at very high RPM, or like 3000 RPM, we need to make sure the wafer stays there. So that's why we use vacuum suction to make sure the sample stays on the chuck. Now first we will cover the inside of the spin coater so that spillage of the photoresist will be minimal. So we will see after that. I am going to cover it. Yeah, now that we have covered the spin coater with the aluminum foil, we will load the sample. Okay, so this is the silicon wafer, okay, which we spin coated last time. Okay, it's a 3-inch silicon wafer that we have. So now we will load it onto the chuck. Okay, so now I have placed the wafer centrally. Now we will switch on the vacuum and also edit the program for spin coating, right? So what we can go to is, there is this run or edit option where you can click it, right? So we already have a recipe set, which means that the rotation will start at from stationary speed. Okay, it will accelerate to 500 RPM, right, in 5 seconds, and stays there. Then followed by rotation at 3000 RPM for 40 seconds, and again deceleration to 500 RPM for 5 seconds, followed by coming back to rest. So this is the recipe or the speed at which we have to spin coat this 3012 photoresist. Okay, now since I have loaded the wafer, I am going to create the vacuum. Okay, so I have switched on the vacuum. Now if you see, the wafer will not move even if we try to push it. That's because the vacuum is on. Okay, now we can go to run mode. Okay, where the if we press start, it will start rotating. Now before that, we have to pour the photoresist over the silicon wafer. Now we will see how the photoresist is coated. Before pouring the photoresist and switching it on, we need to make sure once again that the vacuum is on. So it's on now. So you can see the photoresist, right? Okay, so I am going to pour the photoresist over the silicon wafer. See, it's a very liquid kind of media. Close to 5 ml of photoresist is enough to cover the 3-inch wafer. So you can see that it spreads. It is not as fluid as water, but more like a oil kind of consistency. Okay, now we can close the lid so that while spin coating it doesn't spill out. Right? Good. Now we will start the spin coating process. So if you look at the wafer, it will start rotating now. So you can see the excess photoresist that spilled over to the sides. That's why we have put aluminum foil, right? And you can see now the wafer is rotating at very high speed. It will rotate for 40 seconds at 3000 RPM, then decelerate back to rest. Now the wafer is decelerating. Okay. Now it has come to rest. So now we will move the wafer from the spin coater to the hot plate so that we can pre-bake it. Now the spin coating is complete, so I will take the wafer out. So first we switch off the vacuum, right, so that we can take it out. So I have taken out the wafer, and now we have to keep it for baking for 1 minute in the hot plate. So we need to make sure that the photoresist is pre-baked for exactly 1 minute at 110 degrees Celsius. All right. So that's the pre-bake procedure. Okay. We'll see how it is done. So I'm keeping the wafer. So we will look for countdown for 1 minute. Now the pre-bake step is done so that the the solvent which was fluid in nature is evaporated. Okay. The pre-bake also helps in better adhesion to the silicon wafer or the substrate that we use. Okay, the adhesion between the photoresist and the wafer. Okay, it also improves the chemical resistance and also improves the light dependent behavior of the photoresist, which is very crucial for the next step, which is our lithography process. So now I'm taking out the wafer because it's 1 minute. So now we have taken out the sample after 1 minute. Okay, so pre-bake is done, right? So now we will go for the lithography process. So what we have here is the mask aligner equipment. As the name suggests, mask aligner. So that means the photo mask that we have with the pattern can be aligned with the wafer or the substrate in which we have the photoresist. So it's an alignment process. Okay. Now we have the UV source, ultraviolet source, that is within this chamber. Okay. So this is the UV source that is used to expose the photoresist, 365 nanometer. Okay. Then we also have the microscopes which we use for alignment. So the display from the camera output from the microscopes can be shown on the display in the system, so that we will be able to see the features very accurately. Okay. So in the mask aligner or in the microfabrication process, all the features are in the range of micrometers, right? So we need to make sure the alignment happens properly. That's why we have microscopes with variable zoom and focusing features to align the mask with the wafer properly. Then we also have the mask holder here. Okay, you can see the cavity here. Okay, so the mask or the photo mask actually sits here between the slots here. Okay, so the photo mask can be inserted here, and then we can close it like this. Okay, now if you look here, we have the wafer holder, which is a circular in diameter, right? I mean, it's like a circle. So the circular wafer can be placed here. Okay, now you think about it this way: then the wafer is here and the mask holder is closed like this with the mask, they align together. Now if there is some small misalignment, we will use these adjustment verniers, okay, to align the mask and the wafer. Now when we rotate this, the wafer, the chuck or the chuck with the wafer moves, and that is how we can do the alignment. Now the chuck has some special properties that we will see later. Okay, and similar to the spin coater, you can see the grooves here for vacuum suction. So once the wafer is kept here, it will not move. Now we will see the operation of the mask aligner. Okay, so this is the PC that controls the mask aligner. So I am switching it on. Then followed by the power supply for the UV lamp, ultraviolet lamp. I am switching that as well on. Now we need to switch on the lamp power supply as well here. So when I press it, you can see some numbers written here, okay, which corresponds to the current rating, voltage rating, and the power. So now that the lamp is on, we are going to switch on the equipment. So now the equipment is initializing. Okay. So this is the UV light that you see, this circular ring. Okay. So there's a slot here through which the light is projected. So we know that the lamp is on. So now we will switch on the user interface so that we can control the equipment. So this is the user interface. Okay. Now we can switch off this mask holder lock so that we can load the mask. So now I'm going to load the mask. So this is the mask holder, right? As I explained. Now you can load the mask. Okay. Once it's loaded, I can press this button here. This is the vacuum switch for the mask holder, so that the mask doesn't move. So now I have switched on the vacuum for the sample. Okay. Now the wafer will not be able to move. Now I'm closing the mask holder. Yeah. So it automatically locks here, and you can see it on the green button here. Now what we can do is to align the wafer and the mask, for which we will go to the alignment mode. When it goes to the alignment mode, you can see that the microscope comes and aligns with the mask here. So now you have to adjust the microscope so that you will be able to see the features. Now you can see there is a dark area here and the white bright region here. So this is the right microscope that you see here, and the left microscope that you see here. Here it's like this because of the low illumination. So I am increasing the brightness slightly. Okay. And I am adjusting the field of view of the microscope. So okay, I'm reducing the zoom. Then illumination is too much. Okay. Now I'm going to, you are able to see some very slight features here. See. Okay. Now you can clearly see the features that we have. So these are electrodes, as you can see, a circular device with a linear array of electrodes that you can see. Okay. You can even reduce the illumination further so that you can see clearly. On the right side as well, I am reducing the illumination. So you can see different patterns on the mask. Okay. On one quadrant of the mask we have this kind of a design. On the other we have different design. You might also have another design here. Okay. So depending on our requirement, we can have different designs on the mask. And these designs that you see here are known as the alignment marks. So if we have a multi-step process or multiple deposition, lithography and etching steps, or multiple lithography, lift off and other steps, we will need to align one process step with the other. So for that we use the alignment marks. Okay. Now it's kind of visible. We will be able to zoom in as much as we need. Okay, you see here, we just have to move it, adjust the focus the way we need, so we will get a very clear image. So you can see different kind of features that are available. See, there are different types of designs that are available for alignment as well. So these are called vernier alignment marks, so that we can see slightest of the misalignments. Okay. Now that we have the samples here, what we can do is to do the wedge error compensation. Okay, which includes lifting up of the wafer. Okay, to a stage where it touches the mask. Okay, so you can actually see in the display here. So since this is a dark field mask, the white region that you see is the opaque region, and what you see through the gray color slot is the transparent region, and you can see the wafer there. Now if we zoom in clearly, or maybe you can see it here, so this was the transparent area, right, and this is the opaque region. Now this is blurry here. When you move it closer, you can see the I am slowly lifting the wafer up. Okay, and you can see that there is a change in shade. Okay, now that area has also focused clearly. See, if you look here, see, you will be able to see the shadow of this plus mark very slightly here. But once you bring the wafer close enough, that short shadow goes away. That means both the mask and the wafer have touched now, but we don't want them to touch. Okay. So for that, now we will do the wedge lock. So now they are parallel, and then we can switch on the the z-axis display that we have here. We can set it to 0 because they have touched now, and then we can move it down by say 50 microns, so that there will be a 50 micron gap between the wafer and the mask. So this is known as proximity lithography, where you don't really have to have the mask and wafer in contact. So why give a gap between the mask and the wafer is that the small gap will prevent any photoresist to remain on the mask surface. So we can have a longevity in the mask life. Okay, and then there are other optical properties which is out of the scope of this lecture. But yeah, so now we have the wafer and the mask aligned. Okay, since this is a first mask process, we don't have an alignment process as such, but we just have made sure that the wafer is sitting almost on top of the mask is almost aligned with the wafer that we have. Now next step is to go for exposure. Now before exposure, we need to calculate the exposure time. So that is something you can set it here. Okay, for the power requirements, so the photoresist has to be exposed with UV lamp for specific intensity. Okay, so you can calculate it here as well. So the UV lamp that we have here, okay, has a power of 22 milliwatt, but the overall energy that we have to supply for for the patterning of photoresist is 100 millijoule per second. So that's why we have to expose close to 4.5 seconds to get an overall energy of 100 millijoule. Okay, so that we have set here. Now we can go to the exposure mode so that the exposure can happen. You can see here the system has moved up. Okay, so that the ultraviolet chamber has come over the wafer now. Now we will go to the monitor and press the symbol here, which looks like a shutter. Okay, so once we press this, the UV exposure will happen. Okay, now if you see here, you will see the UV exposure being happening. I'm pressing the shutter button. So this is the ultraviolet light exposure that's happening. Now once the exposure is done, the device will go back. Okay, now the next step is to unlock the mask holder so that we can take out the wafer for the next step. So then before that, we have to make sure the sample vacuum is off. And we have taken out the wafer. Now the next step after lithography or the exposure for a positive photoresist like that we use is something known as hard bake. Okay, sorry, soft bake. So we did pre-bake already, then we did exposure, and now we are going for soft bake. After soft bake, that which happens at 110 degrees Celsius for 1 minute or 60 seconds, then we will go for the development process. Okay, so in the development process is the time where the exposed photoresist, which since this is a positive photoresist, the exposed area becomes soft, right? So the exposed area will get removed. Now that we will see that. So now I will keep the wafer onto the hot plate. So the wafer is being kept at 110 degrees Celsius for 1 minute. So this process is known as soft bake. So I am now taking out the wafer. It's being 1 minute. Now the next step is development. So now I am pouring the solution named as developer. Okay. So developer is a solution which removes the soft photoresist as I told you before. Okay. So and then we also have another petri dish with DI water. Okay. So the development is time dependent. if you keep it in developer or the wafer in developer for long time, the required photoresist also will get removed, or the hard photoresist will also get removed. So as per our process here, we have optimized to close to 30 seconds. Okay, and as soon as the development is complete, we have to transfer the wafer to the DA water bath so that the reaction stops. So now I am placing the wafer onto the developer and agitating it. Take out. Now you can see kind of patterns here. I'm putting onto the DA water so that the pattern is preserved. So now the development is complete. So if you zoom in closer, you will be able to see patterns here. So that shows the lithography is successful. You can see the patterns. Now the next step is to dry the wafer, okay, and then go for hard baking. So now the wafer is dried. So the next step is to hard bake the wafer for 3 minutes at 110 degrees Celsius. The hard baking step will harden the photoresist that remains so that it can sustain the metal deposition process that is going to happen next. Okay. Now the hard bake is complete. I'm taking out the wafer. Now the wafer is ready for metal deposition. So now, so the lithography process is complete. And what you are going to see next is the metal deposition process using E-beam, where we will be depositing titanium platinum, which will be the electrode material. Okay. So goodbye.